Hello, friend. My name is Derek Harder, and in our video today, my goal is I just want to kind of give a little bit of some hints, just some quick hints of how to do programming in C++ for assignments for our class here. So if you're watching this video, you're probably in a class where we're using C++, where we expect that you know how to program, and you're familiar with programming in some various high-level languages like maybe Python or Java or something like that. But you haven't necessarily used C++ ever, or very much. Okay, so in today's video, I'm going to go over some kind of helpful hints quickly of a couple of things about how you compile programs, how you organize multi-file projects in a C++ project, using some of the important C++ libraries. So using the I/O streaming library for doing input and output, using C++ strings, doing some unit testing with the Catch2 framework, using C++ classes, so a little bit about object-oriented programming with C++, and then a bit about using what's known as the standard template library, which gives you some containers like lists and maps and things. Okay, so if you're ready, let's go ahead and get started. Okay, so let's start with just a little bit about compiling. It's a little bit miscellaneous, a few things, but just some ideas about compiling C++ programs. A little bit about the command line usage, and also just a feel about how a multi-file project works in C++. Okay, so let's start with a quick example here. In this particular project, actually this particular executable I'm going to show to demonstrate these things, we've got two files. We've got one file called hello world.cpp. This has a single main function. Okay, so this is the main function in a C or C++ program is the entry point. So there's only one main function that could be compiled into an executable, and when you start running the executable, it's going to start running at main. Now this main program is using a library called mylib. Okay, so we've actually got a second file, a second header file, that HPP file, that defines a function called mylib_greeting, which is implemented in the mylib CPP file. Okay, so I'll come back to that, but we've actually got two source files, two CPP files, and a header file. All right, so usually when you're building a C++ program, you need a C++ compiler. We're going to use the GNU compiler here. So usually for the assignments for our class, you'll have a build system set up. So in this case, for our build system, if I want to build the hello world executable, I can use the make. We're using the make build system. And this will build all the files that are needed. Okay, but I just kind of want to show this from the command line. Okay, so we've got two CPP files. So normally what happens in a compiled language like C++ is you have to compile in a multi-file project, you have to compile the individual source files into what are known as object files. So that's what the first two lines are doing here. And I could do this from the command line. So my compiler is G++. So if I wanted to compile the file called hello world, CPP, my source file, and the -o means I want to output that to a file called obj/hello world.o. Okay, so this is the simplest example of compiling a source file into an object file. Okay, object files are intermediate. So you can compile individual source files into object files, and then we need to link those together to make a final executable. Okay, so this would be sufficient to compile my file, except with one thing. I also need this parameter here, because in a multi-file project, I'm including code. So I'm including code in my hello world CPP from mylib, my library. Okay, so I have to include this header. This header, so when you include files like from the standard library, IO stream, it looks in standard locations on your system to find those header files. But if you're adding your own header file, you have to specify the location where you want it to look. Okay, so that's what the -i command line command is. So there's a subdirectory called include that's, from where I'm currently at, there's a subdirectory called include that has the header file that I also need to include. Okay, so that should be sufficient for me to be able to compile this. So that should be sufficient to actually compile this, although I also forgot one other flag that the -C flag here means I don't want to link together a final executable. I just want to stop it making an object file. Okay, so we're going to compile these files separately since this is a multi-file project. Okay, so the other flags here that you saw when I used the build system are we're turning on some warning flags. So we want to warn on all errors. And we're specifically specifying we want to use the 2020 standard of the C++ compiler. Okay, so I could do the same thing to build the mylib. Okay, so this is another file. We're going to just separately compile it into an object file. Right. And then the final step here, so when you're doing multi-file compilation, if I have separate object files, I have to actually make an executable. Okay, so all this line is doing, it's still using G++, but it knows without the C flag that everything you're giving it, it should link together into an executable. Okay, so in this case, we're linking together the two object files that we created into the final executable here, right? And that's all we need, right? So now at this point, we actually have our executable called hello world in the bin subdirectory. And I could run it from the command line like that, all right? So another thing about this example, let's talk about the command line argument. So if you saw what I just did when I ran this, that it ran here and it gave this message here, a usage message. Okay, so you might be using command line arguments in some assignments for this class here. So in C++, if you're building a command line tool like this, you can provide what are known as command line arguments, and those come in the argc and the argv to the main function, right? So the entry point for your C++ code here. So in this case, argc stands for the argument count. Right, so in this little command line tool, we're expecting exactly 3 arguments. The name of the program is hello world. Then we want an argument which is an integer, which is the number of times to repeat, and then another argument which is the string. Okay, and then the argv is the actual argument values. This is actually passed in as an array of character arrays. So that's why there's 2 pointers here. All right, so this expects, you can see how it works like here. This expects that argv0 is actually the character array of the program name. argv1 is going to be something that we're going to interpret as an integer. Okay, so you see how we do that here. Right, so whatever is the first command line argument, we pass it to the ASCII to integer function to convert it to an integer, and that's the number of times that we'll repeat the message. And then we're expecting argv2 to be just a string. Okay, so let's see how that works in the code here. So if I was to call my hello world, but I said repeat 3 times the string Derek Hart. So when you're doing stuff on the command line, things separated by space are how normally it separates the command line argument. So in this case, I've got the first command line argument is the name of the program. The second one is the 3 here that we'll try to convert to an integer. If you want to have space in your command line arguments, you have to put quotes around it, right? So since I have quotes around this, this will be the 3rd command line argument, a name, which we'll use as a string in this program. Okay. So if we run that, this first output here comes from this line here. So it takes the, so again, this is the 0th command line argument, the first one, the second one. So it takes the second one and it just outputs hello and then name. So this is a simple hello world program. Okay, and then finally, the last thing for this example, just a quick word about multi-file projects like we're doing here. Okay, so in this case, the last repetition of the lines here are done by calling this mylib repeat greetings function. Okay, so the standard convention, if I want to put code into separate files and then reuse them in this file is, so here I didn't implement this function in this file, hello world CPP. I'm reusing the function from where it's declared and implemented elsewhere. Okay, so in particular, this is my own user-defined library. Okay, so when you define your own library or class, you should always have a header file that we call mylib.hpp, and inside of the header file, you put what are known as the function prototypes, or the function signatures of the things that are available in this library. Okay, so anybody that includes mylib.hpp will, when you include it, it's including this, including the prototype of the functions that are available that can be used if you want to by calling them, that are implemented in this library here. So in this case, there's just one function in this library called mylib repeat greeting that takes two parameters, a string and an integer, and it returns a Boolean result. Okay, so because we included this in our hello world.cpp file here, and because we had the -i included so it could find that header file, when the compiler goes to compile this function and it sees that you're trying to call a function called mylib_greeting, it knows what the signature of this function is, so it can compile the hello world.cpp file, right? Because it knows, since I included this file, that mylib repeat greeting should take two parameters, a string and an int, and return a Boolean result, and it should be named that. Okay. But the actual implementation, so again, back to when we were compiling this, we compiled the hello world.cpp, and we compiled the mylib CPP separately, right? So the actual implementation of mylib is in the you always separate the declarations of things from the actual code that implements them. Okay, so in mylib.cpp, there should be the implementation of mylib_greeting, right? So it has exactly the same signature, but instead of being ended in a semicolon, it ends with an opening, closing curly brace, and the actual code for the implementation of the function is found here. Right? So yeah, so that's what I'm. One more thing that I did want to mention. C and C++ are still using the way that you include other code to be reused in your own code is use this include macro. This is part of the preprocessor system. So really all that happens for a pound include is it actually just copies the contents of mylib.hpp. So it has to find the file on your file system, but it's basically like taking the contents and doing a Control-C copy and then doing a Control-V paste, right? That's all that the include does when you do that, like copy and pasting the code, right? That's kind of a primitive way of doing that, right? So newer languages have a much more robust way of including modules and reusing code, okay? But because of that, you have to be careful about including code twice or having things declared twice. So you'll often see what are known as header guards. All right, so that takes the form of more preprocessor macros. So this if not def guards anything here from being included twice. So the very first time we include this code, it will define this variable here. And then the second time, it won't include this again. Okay. Another note, so newer C++ code, you can also use this pragma. It does the same thing as these header guards. This isn't actually defined as part of the C++ language, but this has become pretty much ubiquitous. So almost all C++ compilers support doing the pragma one. So either way, so use the if not def header guards or the number pound pragmas to do this. Okay, so let's move on to the next topic. Actually, I'm going to cover two things in this next example. So for one, in the original C language, if you wanted to represent a string and process a string type, you had to use arrays of characters. And that was a very low-level way of representing a string and processing strings. Okay? If you're doing C++ coding, don't use character arrays. Okay? So in the previous example, I was forced to use a character array because actually the argv parameters that come in as the command line arguments are passed in as an array of character arrays. Okay, so that's why it was the double pointer. Okay, but normally, whenever you're doing string processing or representing strings in C++, use the string data type. Okay, you should never use the old C character arrays unless you absolutely cannot avoid it. Okay, string provides a much higher level of abstraction for string processing and representation. It's much nicer. It's basically like using strings in Python or Java or some modern high-level language. You can concatenate strings, but as I'll show in this example, if you need to do anything more complicated than just putting two strings together, you should use what are known as string streams and use the streaming library if you need to do formatting of strings or formatting of output. Which brings me to, let's also talk about the streaming library for I/O. So you should be familiar with this. Don't use the old C I/O libraries like printf if you're doing C++ programming. You should use what are known as the streaming library. These allow you to do input and output. So if you want to do input and output to the standard terminal, so input from the keyboard, output of the terminal, just include the I/O stream. For basic streams, that gives you the C in and the C out standard input and output. So yeah, that gives you your C in and C out standard output. If you want to do I/O to files, include the F stream for the file stream. So that allows you to open up a file and use it as a source to bring either stream stuff in, so as an input source, or to stream stuff out. Okay, so streams can work either way. So you can have an input stream to stream things into your C++ program, into variables and things, or you can have an output stream to output things to a destination, right? And that destination can be a file for like the file streams, or it can be an input source, or the destination can be a string. So you can input things from strings, or format them and output them into strings using the string streams. Okay, and we'll look at here. So if you need to do more complex formatting, use the IO manip header to get string manipulations, and we'll look at some other things. So when you're opening files, I mean, this in general, whatever kind of file IO you're using, you should always check after you open a file that it was successfully found and opened. Okay, so let's look at this example here. Okay, so in this example, we're going to look at streaming and also at using strings here a little bit. So we're going to include the IO stream, the file stream, F stream, and the string stream, like I mentioned. So we can have examples of each, and also the IO manip library, so we can do a few examples with stream manipulators. C++ includes a modern notion of namespaces, so that you can have things separated into different namespaces, and all of these are actually in what are known as the standard, the basic standard C++ namespace. So if you don't, I usually prefer people, if you're doing C++ coding in my classes, to include this line. So this just keeps us from avoiding to have to explicitly specify all the things that we're going to use in this program in the standard namespace. So if you don't have this using namespace std, everything in the standard namespace you have to explicitly state, that, for example, I'm using C out, but it's in the standard namespace. So without the using namespace, all of the things in the standard namespace have to be prepended with standard : okay. So either way, some people think it's better to always, explicitly note in the programs what namespaces are things in, but I prefer to, for the standard namespace at least, not to have that specified for everything. So here's some examples of strings. So if you want to use strings, actually you should also include the string. But the string is probably included in one of these, which is why this program compiles without it. But it's always a good practice to include all the headers of things that you're using, right? So strings, if I didn't include one of these, this also probably including you're using strings. I would have had to explicitly include the string to use these here. So these are just example strings. So if you want to use some strings in your programs, just use the string type. It's a little bit different from a basic like float or an int, but it's really kind of like a class or an object. But you can initialize it in ways that would feel familiar. So here we have two strings. And as an example of output, so to stream things to a destination, you use the output operator, which is like two left-hand things. So basically, everything you want to stream to something that's open for a destination, output stream destination, just put the output operators to those, right? So here we're going to output like a table here. So the first one is just outputting like the headers for a table. So we output like a bunch of strings, the employee name, department, and so on. But we're using some string manipulators, okay? So the order that these will come out on my output is the order that they arrive. So the first thing that will happen is we will use a manipulator to set the output width for the next thing to be 25 characters. So it will pad the next string, the next output it sees, to 25 characters in length. And then it will left justify. So this will be left justified in 25 characters. Okay, so these are all examples of the output manipulators, the IO manipulators. Actually, only one, well, two: left justification, right justification, and setting a field width. Right. And then likewise, so we're doing the same thing here, but we have a few more examples of IO manipulators. So here, besides setting the width, where we're going to be outputting the actual row, the data of our table here that we're formatting, we're going to set the width. We're going to actually fill these so you can see that the width has been set for the actual data here. And we do some others. For example, we set it for our salary to use exactly two places after the decimal point, and to show the decimal point, and to use fixed instead of scientific notation. All right. So let's show how that looks. We'll look at the rest of the code here in a second. But I'll go ahead and make my IO string. So note that this isn't a multi-file project, so all I have to do to compile this one is to compile the object file and then link it into my executable. And then we'll run the executable like that here. So the very first output here is coming from these two lines, okay? So the first output is outputting the header for the table, and then we output these row of dashes. So we output the row width of dashes here to exactly match the row width of our header and the row width of our data. And then these things here are actually formatting. So the first field is where we're outputting my name, the string here. We're setting the width to be 25, and we're filling anything that we didn't use. So everything that got padded got filled with a dot instead of a blank space, right? So you can see that the first field was 25, the second field was 20, it was also filled with dots. Our third field had a width of 10. We right justified the salaries here, so the decimal points lined up, and we used an underscore to fill up these fields. Right? So let's do exactly the same thing, but let's read in. So here we're going to create a input stream from a file, right? So by default, I didn't show input. So by default, we had C in and C out, but we were only using output stream. So let's have an example of an input stream. But instead of using C in, we will open up a file to be our input source for the stream here. Okay, so as I mentioned before we got started with this example, it's always good practice, whatever file IO you're doing, whenever you open up a file, you should always check that it was successfully opened. Okay, so in C++, when you use the input file stream or output file stream to open a file to become a source or a destination, if the is open method, you can use that to tell whether it correctly opened or not after the open call. So if it's not open, it means that it couldn't find the file or some other problem occurred. So we're just doing a little bit of error checking, some defensive programming. So once we have that open, so notice the file is in a subdirectory called data. And it's the IO string input database.txt that we tried to open up. So this is the format of the file. So actually we expect the first two fields to be the last name, first name, and then one field is the department, and then the next set of input, right, we're just using white space. So the default for the input, the same like on the command line, is it's going to break things up by white space, as we'll see in a second. So this should be the last name, first name, department, salary, age, and then whether they're an adjunct or not. All right. So here's all you do for a input, right? So you can, break up input using an input stream other ways than by using white space. Okay, but the default is to use white space. So if I just stream this, my FN, which is my input stream from the file, into last name, first name, it will take the first field separated by white space, which is this one here, and that will get streamed into a string. It'll try to interpret that field as a string and stream that into last name. Then it will take the next field. So this was our first field. I'll take the second field, Jane here, separated by white space. And that will go into first name. So that's how we got first name and last name out of the file. And then the rest of these, so since the way it does this is it separates by white space by default, and then also if you stream into something other than a string, it will do the equivalent of like an ASCII to an int, or ASCII to float, or ASCII to Boolean. Okay, so the next field that it streams in from the file, the third one, it will interpret as a string for biology, but then the fourth one it will interpret as a floating point value. Okay, so here the first one is the department, it's a string again, but the next one it will stream in, but it will first try to convert it to a float. If it's successful converting that to a float, it will save that into the salary to floating point variable. The next one it will stream in is the age. It'll try to interpret that as an integer, convert it to an int, and put it into an integer variable. And the last one it will try to interpret as a Boolean variable and save that as the Boolean. But then we just output that using exactly the same format we did before, but with this second person in our database, right? So that's where this line came from. But this actually came from reading it out of the file here. Okay, and then as a final quick example here, let's look at streaming to a string instead of streaming to the cout. And also, both will stream to a string, and we'll use an output stream to actually write our full table to output to a file that's formatted in this format here, okay? So as an example of using a string stream, so here we create an output string stream called header out, right? But again, once you have a stream, an output stream or an input stream, you can use it in exactly the same way that we use the output or the input we saw before. In this case, though, the destination for the output is going to be a string, or it's going to be an output string stream instead of a file stream or the standard terminal stream, cout. Well, we do the same thing we did before, but this gets streamed into the header out. So we stream out our header into this header out string stream, and then a row of dashes to our string stream. And then we create two other string streams that I kind of just stream this into the same output string stream, but we've got a separate string stream where we capture the string from the first employee that we had, and another one for the second employee. And then here, notice we output those. So the header out, E1 out, and E2 out are both string output streams. So we can convert those to actual strings by calling the .str, the string method. Okay, so these get converted to actual strings and then get streamed to the cout output string. Okay, so that's where the second output is exactly the same formatted output, but these are coming from the header out string stream, the E1 out string stream, and E2 out string stream. Okay? And we can do exactly the same thing now that we have these in string streams, but we can send it to an output file stream. So here we create an output file stream to the file data io string output table.txt. Open the file, we check that it was correctly opened, and we just stream those string streams again to our file output stream. So the result is the this table here, io string output table.txt. Gets formatted exactly the same as our two outputs that we saw on cout, but it's in the file. Okay. Okay, so in our next example, let's look real quickly at doing object-oriented programming in C++ and C++ class. Okay, so you know, if you're not familiar with object-oriented programming, you know, you might want to go and review that a little bit in more detail than what I'll give here. But basically, in object-oriented programming, a class encapsulates the state of a single object instance. Okay, so typically the way that that works in a C++ class is that all member variables of a class would typically be private in order to protect the state of the class. Things that want to use the class need to call member functions of the class. So member functions are going to be public, and there's going to be some public member functions that can be used to see what the current state of a object is and to modify that state if needed. So like our multi-file project example, the declaration for a class should always go into a header file, a .hpp file that holds usually the C++ class declaration. And then all implementation of member functions of the class should go in the corresponding CPP file. So that's where you'll have the actual implementations of the member functions for a class. So usually then, I mean, you have to have some things that are public in order to use the class. So the most basic example of those that you'll see in this example are setter and getter methods, so that we can get the state of certain information about an object, and if we need to, we can change that state using a setter. And then a final example here. So in C and C++, one of the powerful things about the C++ language is you can actually manage, do your own memory management. So that's both, makes it powerful, but it can be a complexity. It can be a curse to do that correctly. Okay. So the most common form of memory management when you do C++ object-oriented programming is any memory that needs to be dynamically allocated by a class is going to be allocated in the class constructors. Okay? And then when the object goes out of scope, something called the destructor is going to be called on the class, and that's where the corresponding delete to free up dynamically allocated memory happens. Okay, so we'll see an example of that in this next example as well. So let's start by looking at the header file for this process class that we're going to use as an example for doing object-oriented programming with C++ here. So as usual, we've got the header guard around this, okay? So, and we've got our declaration of the class down here, although, you can have more than the class declaration. So things that are used by that class might be declared in here as well. So in this case, we've got a couple of type defs in order to make the code more readable. So since process identifiers time and priority should never be negative, that we're going to use unsigned ints, but to make the code more readable, we do a type def. Likewise, we could have the valid states for a process are just one of these five. So these are what are known as an enumerated type. You shouldn't use just like integer 1, 2, 3, 4, 5, or even use like a pound define. So the old way to do an enumerated type like this in C was to use pound define new as 1 and so on. Use preprocessor macros, but you should use the enumerated type if you are trying to add a new data type that's limited to a certain number of it. Behind the scenes, it does the same thing. So like it probably assigns 0 to new and like 1 to ready and so on. But the enumerated type is more readable. Okay? So let's look at our declaration. Okay, so again, there's no implementations here. So the process class, so a class in C++, consists of things, the name, and then things between curly braces, and then kind of like the function prototype or signature, you end a declaration like this with a semicolon for a class declaration. But then you use the public and private keyword. So all these things down here are actually member variables of our class. So a process, the state of a process consists of the identifier that was assigned to the process, what its current state is, whether it's ready or running, how much time it's used so far in the system, what command it was used to invoke it, what its current priority level is, and open file IDs. Okay, so that's the example of the private state that we're going to have for our class. And then to manipulate that state, we're going to have a set of getter and setter methods. Okay, so these are all public. So we can actually get asked to get any of these, almost any of these. So we can get the process identifier, get the usage, that kind of information. And we can set a couple of these. Like we can set the next state for the process or set the current priority for the process. And then this is common in a lot of object-oriented programming languages. So you'll see equivalents in Java and Python. In C++, you can create what are known as constructors or destructors and destructors. So they have just the same. So to specify something as a constructor or a destructor, it should just have a name that's exactly the same as the class, right? And the destructor just uses the tilde in front of it. So that means that this is the destructor. The destructor will never have any parameters. You could have multiple constructors for a class. So in this case, we've only got one constructor. So to create a new class, a new process instance, you always have to have the process identifier and the command that forks the process specified when you're creating the new process. All right? So that's kind of what this means here. So then given the declaration, the implementation should always go in the corresponding CPP file, process.cpp. Right? So if we look in here, I won't go through all these one by one, but you'll see that for each individual one of those, for the constructor, the destructor, and then we've got our getter methods, get PID, get usage, and so on. We've got the actual implementations of each one of those member functions. All right. So the way, remember that namespace idea that we talked about, when you create a class, it automatically defines a namespace for it. So basically this is saying that these are not regular functions. These are functions that are members of the process namespace. Okay, so the get PID is not just a regular old C function or C++ function. It's a function that's a member of the process class namespace. So it's a member function. Right? Otherwise, these have the same as a regular function, right? So all the getter methods, they don't take any parameters, but they return a value. So this returns a time or a priority for the get priority. Whereas all the getter methods are usually, they don't return anything, but they take a parameter's input. So the set state, you have to pass in the new state. And then this is typical for the constructor and the destructor. So the constructor just initializes all of the private member variables, right? So the process identifier and the command are initialized as are specified in the parameters here. And then state, usage, and priority get initialized to the default values when a process starts out. And then the file IDs are actually dynamically allocated, and we need 10 of those in this example here. So we just dynamically allocate an array of 10 file IDs, and we initialize a couple of them before we start. And in the destructor, since we dynamically allocated some memory in this class, whenever a process goes out of scope, so whenever a process is deleted or destroyed, the destructor will automatically be called, and this will call the corresponding delete to free up this memory that we allocated with the new when we constructed a process. Okay, so let's just see that working in practice here. And also, an example of some unit testing here. So I'll go in a little bit more detail of unit testing in a second here. So for now, let's say that I want to test out my processes working here. Okay, so notice what we're doing here is here's an example of creating an instance of a process, right? So to use the process, like we showed before, this is a multi-file project. So I need to include my process header file. So that includes everything I need to know in order to create an instance of a process and call member functions on my instance, right? So here, if I create a process, the only constructor that was available was the one that took the two parameters, the process identifier and the command that was used to fork or create that process. Right? So here we create our process identifier and our command, and we create an instance of our process. Right? So whenever you create an instance of a class of an object, it's like defining a new variable. Right? So classes work like adding a new data type to a language. So now that I've define this process class, I can create variables of type process and create instance of those. Right? And then, once I have an instance of a process, I can call any of those member functions. So we expect that if we create this process 1 here with a process ID of 1, that if we get its PID, that it should have that same process identifier. If we get the command, it should have that same command. And then since it's initialized in the constructor, we expect the usage to be 0 initially, the state to be new, and so on. So this is just testing out that the constructor is working. And also this is just testing out that, you can have as many instances of processes as you want. So here we create a second process that has a process ID of 2, and we test it out, that it's working. Right? So anyway, that's the basics of a class and stuff. So let's go on and let's look at a little bit more detail about this unit testing stuff that we had in this example here. So in this next example, let's look at a quick example of doing some unit testing in C++. Okay, so we'll do this with the Catch2 framework. So, it's common to do this kind of testing now in modern programming, and you'll probably have to do it for our class. So I just want people to have kind of a familiarity with what we mean by unit testing and how it works here. So let's look at another example of a library that we might want to test here. Okay, so we have a library for a multi-file project called mystatslib.hpp that defines 2 functions. One to calculate the mean. So given an array of values, it should calculate an array of float values. It should calculate and return the mean of those values. And then a second function to calculate the standard deviation. So given the same kinds of parameters, an array of values, it should calculate the standard deviation and return that as a result. Right? So these are our declarations in our header file, and these are our implementations. I won't go through these, but so we have some code here to take an array and calculate the mean, and another set of code to take an array and calculate the standard deviation. Right? So let's say we wanted to test that library. Right? So in this example, we're using the Catch2 framework. Okay. So to use the Catch2 framework, if you include the catch HPP file, the catch HPP header file actually has its own main function. Okay, so it defines a main function. So we don't have to define a main function in any of the source files that we're going to link together, because when we're using the Catch2 framework, it has its own main function. And many other unit testing frameworks do something like that, something kind of similar. But that's all we really need to do to use the Catch2 framework, is include this here. Once you include that, you also have these other things. So in particular, there's lots of others. I'm not going to show the test cases and using the check here. But so since we have 2 simple functions that we want to test, we're going to create 2 test cases to test the mean and standard deviation function here, right? And again, since I want to reuse those functions, I also have to include my own library from the mystatslib. So in this case, a test case, everything that you check, basically, it's going to be a Boolean result. Okay, so if the result that you ask it to check is true, the test will pass. Okay, the check will pass, and if it's not true, it will fail. And as you'll see here, when you run these tests, you'll get a notification of which test passed and which test failed. So, for example, our first test here, we expect that if you give it a list or an array of values where you only have one value, the average or the mean of one value is just that same value, right? So this is saying that if I call the mean function on this array with just a value 1.0, it should tell me, it should return a result of 1.0 when it runs. Right? So let's see if that's the case. So there's various ways in projects or assignments for this class that you can run these unit tests. You can run these from the command line. Let me go ahead and build this from the command line and run it. So if I wanted to, I can make my executable here, build everything from the command line using the make command, and we can run the test. So this actually created the executable called that. So to run it, this will invoke the main function that's included by the catch2 framework. We can run it like that. So right now, all the tests are passing. Okay? So if you're using Visual Studio Code, in my class, you should also be able to run these from the test runner here. So this may or may not be set up for you correctly, but if this is set up, it'll detect that it's got a unit test executable, and you can run it from in here. It should be running the same executable, and we should get the same results. Although using the test runner is kind of nice because it will mark up your code here. So nothing is actually failing right now. So notice we're getting green check marks. So both of my test cases are completely passing all their checks here. Okay? So let's break something just to show that this is actually working the way that we were expecting. We had actually, so I'll break something. We'd actually given like a special case. We'd define that if you pass in an array that's empty, so an array with that the number of values is 0, we expect that you should just define that to have a mean of 0 for an empty array or empty list of values. Right? Let's say we hadn't implemented that test case. But it should pass everything else. So it's still calculating the mean correctly for when we have an array of one or more variables, but not for our special or edge case. So let's recompile that. Okay. Cut there, check. All right, so let's go ahead and rebuild this after we introduce a bug here. So I'll do my make for everything again. And let's try running our test. I'll run it from the test run this time. So when we rerun here, so notice that we're not all green anymore, right? So we're failing something on the mean. So we can click on that and see what we're failing. Right? So here, again, it's nice using, if you've got the test runner set up, or, we could have done that from the terminal. We should get the same result. So when I run it from the terminal, it's indicating that only one thing is failing, the one on line 46, my stats lib. So here, it ends up returning not a number instead of 0. So this would allow us to go in and debug or realize that, oh, we forgot to add in the special case here for when we pass in an array of size 0. Okay, so in our next example here, I want to look just mention a few things about using the standard template library in C++. So the standard template library, if you haven't used C++ before or don't think of it as a very high-level language, this is what basically provides the data types that makes it equivalent to using something like Python or Java. So C++ is still a little bit crusty in its syntax, but the modern set of containers and data types that it provides in the standard template library are on par with the usability, the abstraction level that you would get in like Python or Java. So in these examples here, I wanted to look at a few examples of the sequence containers, so like the lists, the vectors. I want to look at the associative containers, maps. There's a couple of things other things like iterators and algorithms and functors that I probably won't go over here, but those are some other things that you might want to become familiar with in the standard template library. So let's start by looking at some quick examples of doing the sequential containers. Okay, so we'll look at the array data type, the vector, and the list here. Okay, so let's start with the array container. Okay, but before I begin, it's a good idea to have something that works as a reference for you for the C++ standard template library. I usually just use the c++.com here using their containers here. So let's bring up the reference for the array class. Okay, so arrays are basically kind of like a wrapper around the regular C or C++ arrays. Okay, but they have some advantages. So I should really start using these more, right? So instead of just using, so instead of just declaring like an array like this, if you're doing C++ code, it's probably better to go ahead and get in the habit of using the array container, right? These are wrappers around the arrays, so around these old style C arrays. So if you're familiar with these, you can do all the same stuff with an array standard template library container. So in this case, we're creating an array of integers of size 5, and we're initializing it to have these particular values here. So we go ahead and compile this example here. And I'll go ahead and run it. All right. So the normal indexing operator. Okay, so this is really kind of wraps it around in a class. Okay, so but you can use it just like an array, as you can actually use like list and vectors kind of array, because the index operator is defined for these here. So I can iterate it over it normally like we would. So if I have 5 items, I can create a for loop that goes from 0 to less than 5 and output that. So that's where the first set of outputs is coming from here. But you can use the new range-based indicator. So with this, you don't actually the size of the array is kept by this sequence container here, which is kind of nice, and you don't actually have to pass in the size. So here you can use what are known as range-based iterators. So this will give kind of the same effect, although if you do need to actually know the index, you'd have to define like an I anyway to know what the index is of each value you're accessing. But in this loop here, since it's an array of integers, each time in the loop, my int will be the next integer in sequence from the 0th to the 4th one in the container. So we'll get the same values out by iterating over it using the range-based iterator. And you can access using the indexing, or you can use member functions. So here, if we look at the member function, I'll go back to my reference documentation here. These are all the kind of the member functions here. So usually, again, I probably won't talk too much about iterators in this, but the ones that you'll mostly want to use will be the things that aren't iterators. So like capacity, so we can find the size of the array, whether it's empty or not. The indexing operator is overloaded, so you can use that, or you can use the @. These are actually equivalent, but this is like using a member function version. And we can get the first or last item, the atom at the front or the back of the array. So just a couple of examples. So here we're showing using that @ to get the same element. So we get the element at the begin at index 0 and index 4 using indexing or using the @. But arrays can't be resized. Okay, so they are like an old style C array. So if you attempt to, for example, access, but they are safer. This is kind of relatively new. It used to be that it didn't actually put this safety for you, but if you try and access element, so again, the array is of size 5 here, so any index 5 or greater is actually illegal. It's beyond the bounds of the array. So if you do this for just a regular array, it won't stop you from doing that. So your program might crash, or it might just end up corrupting memory. But if you do this with a standard template library array, it actually throws an exception, right? So we're actually getting the catch here, the out of range exception, trying to access or set the element beyond the bounds of the array. Okay, and then so arrays can't really change dynamically, so they're not as useful as like Python lists or lists that you can get in Java or other languages like that. So you might want to have something that can actually grow and shrink dynamically. So that's really what vectors and lists give you. Those are the only other two kinds of sequences that I'll talk about. So if you want a vector of integers, we can declare it like this. And again, if I didn't mention it, to use any of these, we have to include the appropriate header. So we include the array, list, and vector in this example here. So in this case, this would be a vector of integers. So we don't give it a size, it will resize as necessary. All right. But the vector, if we look at our documentation for the vector, again, I'll just quickly look at the member functions that we have. So besides the iterators and the constructors, it also has like the size and the capacity and whether the vector is currently empty or not. And then it has these pushback and pop back, so that we can actually grow the vector one by one, element by element. So a vector can grow dynamically, but it actually does use a block of memory. So it's really behind the scenes using the same kind of allocation like an array. So if you grow it, it might have to actually reallocate a new array and copy stuff over. So it can be a bit inefficient at some times when you grow it. But so let's just show some examples. So you can use it the same way as the basic array that we showed, right? So it defines the overloaded indexing operator. So I can get like the third element. So from this point on is where we're getting output from calling the my vector here, right? So if I want to assign element 3, I can assign it and access it like that. I can also use the at. We can ask for the size of the vector. So currently it has 5 elements at this point here. That's where this is coming from. We can iterate over it. We could iterate over it, again, using indexing and using the size, or we can use the range-based iteration, same way we did before here. Here we showed using using indexing by an explicit index I here to get the values. So that's where this output came from. But we can grow and shrink it. Okay, so right now in our code, the size and the capacity, I should have said max size and capacity are different. So the size and the capacity are both 5 since we initialized it with 5 items. So if we push an item on the back, notice that after we do that, the size is now 6 and it doubled the capacity. So basically, whenever it needs to grow a vector, it will reallocate the array, but it will allocate twice as much space as before, right? So we're only using 6 of the 10 allocated integers that we have in the vector right now. So that's because, so now pushes until we fill it up again won't take any performance hit. So if I push another value on the back, it won't have to reallocate. Now we'll have 7 values on there. So you can actually like remove things from the middle of a vector, or insert things in the middle, or even insert things at the front, right? You do have to use these iterators, right? So like if I want to remove the item at index 2, you have to find the beginning iterator and say +2 to that. So that's the same as going to the item at index 2 here. Okay? Again, these aren't going to necessarily be very efficient either, although these are always going to be kind of inefficient, because if you're removing an item from the middle or inserting an item in the middle, it has to shift the item. So beyond, so if you're inserting items, it might have to grow the capacity, but it always has to shift the items to fill up holes, or shift the items to make a hole so I can insert something in the middle. So anyway, after we pushed 55 and 66 in the end, and we removed the item from index 2 and added this item, if we iterate over again, we now have this one. So we've got like 7 items in here with 55 and 66, and we had put like 99 at index 1 here, which shifted all these down to index 2 and beyond, and so on. Okay, so and let's also take a quick look at the list sequence container, since we're talking about sequence containers here. So a list is implemented as a doubly linked list. So it's good, to maybe think back, review your data structures class. So this will kind of tell you why, why you would want to use a list versus a vector, and when they're going to be efficient or inefficient. If you understand how it's actually implementing behind the scenes, the data storage is doing. So since it's using a double linked list, and it's keeping track of the end and the begin, it's very efficient to insert elements on the front or the back of a list. Okay, so you've got push back and push front, and pop back and pop front. Okay? And it's relatively efficient to insert items or remove items in the middle, although you have to find the item first. So you might have to do a big O of N iteration to find the item that's internal to the list that you might want to remove, or the location where you want to insert an item. But if you have that location, you can easily insert a new item because it is a linked list. So you can create a new node in your linked list and insert it into the position that you want in the existing linked list data structure. All right. So the list then allows you to a lot of the stuff that we showed before, all the stuff that we showed before, you can kind of do similar things. I think that the list has the indexing operator. No, it doesn't, because it's not really efficient to go to an item in the middle of the list, right? So if I'm going to get the item at index 3, I actually have to iterate. I have to start at the beginning of the linked list and iterate to find that index. So it doesn't actually support the indexing operator. You'll notice that's not loaded, nor the .at member function. So you can mostly only want to work at the beginning or the end if you use the list data type. Right? But if that's all you need, if you only need access to the beginning or the end, it's easy to push and pop, push things on the front or the back, or remove, pop things off the front. So in this case, and you can iterate over using the range-based iterator, though. So you don't have the indexing operator, but you can iterate efficiently in the same way that we did for the vector and the array. That's where we get the result here. So we have 5 values, 1, 3, 5, 7, 9. We get those out here. So if we push an item on the front and the back, and we iterate over it again, we've now got a list of size 7. We've got 42 at the front and 52 at the back. All right. And we can remove those items back off. So here we just show taking the 2 items that we put on, taking them back off again. So we're back to the list of size 5. Values. Okay, and for the next example, let's look at associative containers. Okay, so if you're familiar with Python or Java, especially Python, you might have used a dictionary in Python. Okay, Java it's not quite as well supported. It does have a similar hash map. Okay, so associative containers are key value pairs. Okay, and we can access, instead of accessing something by its index, integer index, like an array, we can get the value out by the key. Okay, so we use the key in order to look up a value in a dictionary or one of the associative containers. Okay? So in C++, the map provides a basic associative key value pair. So we can insert and retrieve by keys. So for example, you can actually use a string as the key, as we'll see here in our example. And we'll also look at the unordered map here. So a map is actually using something like a binary tree. Again, if you remember your data structures class here, so that actually allows us to iterate over a map sorted by the key values, right? So you can actually iterate over it in sorted order by keys. You don't always need that. You don't always need to be able to iterate over an associative container like this. So a binary tree takes about log n time to insert or look up a value. So you can get a little bit better performance by using a hash table. Okay. So an unordered map, you can't iterate over an unordered map in sorted key order, but you will use a hash table behind the scenes, which means it's basically constant time, usually, to insert or look up a value in an unordered map. Okay, so let's really quickly look at the reference for the standard template library map. So there are associative containers that use something like a binary tree or probably like a red-black tree or something like that. So if we look at an example, like maybe we'll just look at it does overload the indexing operator again, right? So let's look at our example here. So if we want to use a map or an unordered map, we have to include the appropriate header as usual. So here, as an example, let's say we want to have a dictionary or an associative map that maps names of people to their birthdays. Okay, so in this case, and we'll initialize it. So basically, key value pairs are what go into a map. So these are these are defined as a standard template library pair. Right. So in our pairs, we have a string as the first item in the pair, and an integer is the second item in the pair. So initially, this map has 4 key value pairs in it. You can iterate over this. So since this is an ordered map, if you iterate over this, they should come out sorted by the keys, right? So alphabetical order in this case. So if I build this example here, and run it, you'll notice that the first set of 4 outputs is coming from here, and it will be pulling these out sorted by the name, basically. So DJKS. But notice, and you know, I kind of hinted at this. This is an example of using the new auto keyword. It's a relatively recent addition to C++, but this is actually a pair object. So to get the key and the value, it uses a member field called first. That's going to be the key. That's how we got the name out of the key value pair here. And then the member field second actually holds the value here. So that's going to be an integer for this map that we have. So there's lots of different ways you can actually add items and remove items from the dictionary. So again, I refer you to the reference documentation, so you can see, you know, we've got the overloaded indexing operator. You can find the size of it, whether the map is empty or not. You can insert and erase items, do a couple of other things with your maps here. So, so for example, I usually just use the indexing operators overloaded, so you can actually use that to insert new items, right? So, or this will actually change the value of an item. So if Kevin was already there, that would just update their birthday. If it's not there, if that key isn't there, it'll actually insert a new key with that value in there, right? So now we've got that key in there. birthdays is not currently empty. After we inserted our 5th item, we've got 5 items in our map. So right? We can erase items, and if you need to, usually, I know this isn't a well-named function. This is just being reused for reasons. But the count is probably the best way if you need to check whether a key is currently in a dictionary or not. So count will return 0 if the key is not in the dictionary, or you can treat that as false, and it will return 1 if the key is in the dictionary. So based on the count, 0, 1, you can interpret that as we currently have that key or we don't have that key in our dictionary. I won't spend a lot of time on the unordered. So the only real difference with this one is that you'll see from the output is if we iterate over the unordered, you might not see it in the sorted order. Okay, so yeah, this comes from that. So it definitely didn't come out here. I mean, it could by chance, but there's no guarantee of the order when you iterate over an unordered dictionary. Right? Everything else is going to be the same here, although, again, this is actually using a hash table behind the scenes, so this will usually be more efficient, although you won't notice the difference unless, you're really talking about large databases here, where you see a difference between login and constant time performance here. Okay, and as one final example, let's look at the queue stacks adapter and priority queues here. So you might be using that in the class that you're maybe watching for this video here. So, so queues and stacks are really adapters of what are known as container adapters. So again, we can look at the documentation for like the queues and stacks. So I'm going to start with the stack here real quickly. So this just defines the standard last in first out for a stack, right? So that means that we're always going to push on the top. It actually implements a push and a pop method, okay? But it basically, it's just a wrapper around a container. So any container that supports getting the back item and pushing and popping on the back can be used as the actual container for a stack. Okay, so we looked at the vector in the list. So you could actually use a vector in the list. By default, it uses a deck. I didn't show that, but a deck is a double-ended queue here. Works similar to like a list. So, if we want to stack, we create like a stack of strings in this case. And here, though, I mean, since we're using the stack adapter, it's only going to be using these member methods that I just showed here, right? So it has the default API for a stack. So push and pop on the stack. Check where the stack is empty. Check what the current size is, so the current number of items that you have in the stack. Right? So here, if we first push on this item followed by this one and this one, you'll end up with the last item that you push is the one on the top of the stack, right? So by design, you can't actually iterate over a stack, all right? Because you don't normally, that's not the way you use a stack. You don't look at the items in the middle of the stack or manipulate them, or you definitely don't remove items from the middle, right? So that's why those weren't defined as part of the stack adapter. You can only push on top and pop off top and get the item on the top of the stack. All right, so let's go ahead and compile this. And run this here. All right. So starting with here, we didn't initialize anything on the stack. So initially it's empty. So initially the size is 0, and if you ask for empty, it's true, right? Empty just returns a Boolean true or false to tell you whether the stack is empty or not. So after pushing these 3 items, again, we can't iterate over them, but you can only access the item at the top of the stack. So, after that, we've got now our stack is size 3. It's no longer empty, right? And we can't access the top item using the top number function. So the top item was the last one we pushed on, the one that said, the string that said I'm on top here. If we pop one item off, we now have 2 items, and the item on top is the second to last item that we put. Right? And if you want to, right, so there isn't like something to clear out the stack. So if you want to clear out a stack, you actually have to. I don't think there's something to clear out the stack. So yeah, if you want to clear out a stack, you have to actually just iterate over it till it's empty. Right. So like we show here. So as long as the stack isn't empty, we just keep popping stuff off. So after we're done with that, the stack is size 0. It's now empty. Right. Likewise, there's a queue adapter. So the queue adapter needs a container that you can push onto the back and pop on the front, right? So that should make sense, because the normal way we think of a queue is you enter the back of the queue or the back of the line, and once you're at the front of the line, you are the next one to be serviced, okay? So it's a first in, first out data structure. Right? So the adapter only defines pushing. They'll push something on the back. You can access who's at the back of the line, who's at the front of the line, but if you pop, it'll remove the person or the item that's at the front, the one that's been waiting the longest, and service them next. Okay. So yeah, again, I don't think I'll go through the details. You can't iterate over the queue, but if you push on 3 items onto the queue, the first one you push on is going to be the one at the front of the queue when I start looking at the front here. So the first one on the queue, if we check the front, is the queue first item. Okay. And one final example, I did want to mention the priority queue standard template library container. So this might be useful if you're watching this video for the class that you're currently in. So the priority queue, if you're not familiar with these from your data structures class, in the standard template library, is actually part of the queue library. So you just have to include queue to get a priority queue. Okay. So priority queue, the underlying container, it actually has to do something like a heap. Keep like a max heap in order to do a priority queue. Okay, so it has to be accessible through this random access iterator and support like the pushback and the pop back to add items onto the into the queue. Okay, so if you're not familiar with it, basically there's going to be some notion of what has the highest priority. So the item that's going to be at the front or that you pop off of the priority queue is going to be the one with the highest priority, however it's defined. Okay, the default is to use just the greater than operator for the type. Okay, so or sorry, less than, yeah. So by default, it will use like the less than operator for the type. So let's say that we want to have a priority queue of our processes in order to build a priority-based schedule. Okay, so in this case, I'm using that process class that we looked at before. So we included the process header file, right? So if we look at the process header file, we mentioned it before that it had a property called priority, and it had a getter method to get the priority. Okay, and we're going to define that a higher number means a higher priority. So if you have a priority of 10, your higher, you should run before something with a priority of 9 or lower, right? If you have a priority of 0, it will be the lowest priority that we can assign. Okay. So for our priority queue, we want to create a priority queue that's a priority queue of process pointer. We're going to put pointers to processes on there. And we specified that we're going to use a vector for our priority queue. And I'll come back to this here in a second. So here we create 3 processes, and the default for a process is it sets the priority to 5. So if we don't specify a priority, these would all have a priority of 5 initially. But then we set process 2 to have a priority of 10, and process 3 to have a priority of 0. Okay? So that means process 2 right now has the highest priority, process 1 has the middle priority of 5, and process 3 is the lowest at 0. And then we just push all these on the priority. We actually push the pointer, the address of each one of these onto the priority queue. Okay. So this third parameter here specifies what's known as a functor to do the comparison, right? So this, it expects to have 2 process pointers, and it will tell which process has the higher priority by using the less than operator here. So this is actually the correct one. It might seem a little bit backwards, but that's the way it's defined, right? So by returning true that the left-hand side is less than the right-hand, we will order them so that the one with the highest priority comes out first in this using this functor here. Right? So that's the third parameter that we passed in when we created our priority queue container here. Okay? So the result, so we can iterate over or in this case, we iterate over the queue, and we take the top item from the queue and pop it off. Okay, so the way we expect priority queue to work is that the first item that ends up at the top of the queue should be process 2 with priority 10, and then the second one will be process 1 with 5, and the third one will be process 3 as priority 0. Right? So that's the output that we get from the priority queue. So again, by using this functor to do the comparison, we ordered stuff we defined the ordering to be the process priority for our queues of our priority queues of processes here. Right? So the first item we get that's at the top when we initially have all 3 items is process 2 with a priority of 10. And then, so after we pop off that item, that removes it from the queue. Then the second item that we get off the queue is the one with priority 5, and so on. Right? So priority queues are very useful. I mean, especially, that's directly what you need to do if you're doing a priority-based scheduling in some class. Okay, so that's it for the examples for this video. Just a couple additional recommended resources. So besides the C++.com for as a reference, works okay for me, just as a general reference for the C++ standard template libraries and other standard parts of the C++ library. It does also have tutorials, especially the standard template library tutorials are fine. Some of the tutorials are a little bit okayish on C++.com. Some of them are better than others. Some of the examples that I was going over here came from or were motivated from this programism.com, which it is kind of a paid site, but it does have a bunch of free stuff with the basics, so you might find a few more details or a few more succinct things about STL, strings and streams and stuff like that on the programism.com on the C++ getting started. Just to kind of summarize, this video is a little bit longer than I was hoping for, so you might want to use it more as a reference than trying to go through it for end to end. But we do cover some of the basics of a couple of things that would be useful for somebody that's doing assignments in one of our classes here that's using C++, and maybe you haven't used C++ that much or not are familiar with it, but you do know, you should know kind of programming in some languages. Python or Java or something like that, okay? So the basics that you probably should familiarize yourself with to use C++ are how to do sort of multi-file projects and why there's things like header files and why you separate header files from implementation files in C++. you should get familiar with the streaming library. So don't try and use the old C printf if you're doing C++ programming. Use IO streaming library for C++ IO. And definitely use C++ strings. Okay, so the old character arrays is not a high-level way of representing and processing strings, right? You should use the new C++ string type. C++, again, because of when the C++ language was defined, doesn't have as much built-in support for doing like unit testing and unit test frameworks. So, we showed some examples of Catch2 framework. There are others. Catch2 is kind of a nice basic one. Gives you the idea. So, if you're doing assignments and like classes that these videos are meant for, you'll probably have to be familiar with what we mean by unit testing and how to use the Catch2 framework. Object-oriented programming in C++ is kind of built in as a basic of the language, so it has the same features you would see in a modern object-oriented language like Python or Java. It's a little bit more crufty, so the syntax can be a little bit stranger, but you should at least be familiar with defining classes and encapsulating private state as member variables versus how you expose the private state for an object instance through things like getter and setter methods. All right, and then finally, you really need to be familiar with the standard template library. So that's what provides the high-level kind of containers to make C++ a modern, high-level language. Right, so you get all of your things like dynamically sizable lists and vectors. You also have associative mapping containers, so the maps and the unordered maps. Plus, there's other things that I didn't really talk about in this video, including other things that aren't containers, so like algorithms for sorting and finding the maximum value and copying things around, stuff like that you probably want to become a bit familiar with if you want to use modern C++. All right, so that's it for this video. I hope some of that stuff was useful. Like I said, maybe this isn't really meant to be used from beginning to end. So you might want to use and go to the particular sections if you want a little bit of help to get started on becoming familiar with the basics of C++. And that's it, and I hope to see you again in the future.